out the volumes, or the volume changes. We're going to average out the molarities. What we want to see is we want to see the spread on the molarities. You know, what kind of precision do you have? And so if you have high precision, what that means is that the spread is very tight. That is, your individual molarities are close to one another. If you have poor precision, that means the individual molarities are all over the place. You know, and it's hard to see what that target is. And so we want to see the individual molarities here because normally when you're given an average, let's say, you know, you aren't given a lot of information. Let's say the class average was 60, but what it doesn't tell you is the spread. You know, for example, were most students right there, or a little bit above, or a little bit below, or was it all over the place? Like some were at 0, others were at 120. You know, and so normally when we write an average, we don't just write the average. We include a statistical quantity along with the average called the confidence interval. The confidence interval is similar to orbitals. You know, what is that boundary called that defines the shape of the orbital and the size of the orbital? Yeah, good, Jason. It's the 95% boundary, and that means you have 95% chance of what? Yeah, finding the electron inside that boundary or within that boundary. Well, the same thing we do with averages. We include a statistic called the 95% confidence interval. The 95% confidence interval, we state the average plus or minus the confidence interval. And sometimes the confidence interval is tight, that is, you have pretty good confidence in that average. Other times the confidence interval is very broad, very wide. That means there's a lot of uncertainty in that average. And so what we're going to do is we're just going to eyeball it. But what we did was we did a calculation, which was the percent difference between the largest value and the smallest value. You know, and that percent difference gives us kind of an idea of how our precision was. You know, for example, if the percent difference between the largest and the smallest was very large, then our precision isn't so great relative to a percent difference that's fairly small. Normally we don't use the percent difference to define the statistics of the average. We use the 95% confidence interval, but I'm not going to talk about the calculation of the 95% confidence interval. That's something that's easy to calculate. And if you have Excel, it can calculate it for you. You don't even have to punch out the numbers. I don't know about Sheets. I'm sure Sheets does it too. Okay. So anyway, we get the average here. If you have, let's say, if you had to do 4 runs, and because the percent difference was too large, greater than 0.5%, then you could eliminate the outlier. Normally we have another statistic that allows us to get rid of outliers, and we don't normally eliminate those, but in this, for this case, you had to eliminate the outlier, possibly in order to get that 0.5% difference. There's some questions here. You can give those a shot. Yeah, do these questions as well. This is just asking what errors would impact the results, the molarity. All right, so I got this question from Calvin. Did anybody figure out how to do this calculation? The percentage acetic acid by mass. Actually, maybe I should ask, did anybody try this calculation yet? No? Okay, then that explains. So it's the percentage of acetic acid. We want the composition of this. And so what we just do is we just get the mass of acetic acid. Divided by the total mass. The total mass is what we call the solution. The solution is a mixture, so the mass of the solution. This is the acetic acid solution. This is pure acetic acid. So sometimes what we do is we put in some additional. When somebody says acetic acid, are they talking about the acetic acid solution, that is acetic acid mixed with water, or are they talking about pure acetic acid? Well, up here they're talking about the mass of pure acetic acid. Down here they're talking about the mass of the acetic acid solution. So anyway, I wrote this maybe equation a long time ago. The percent A by mass is equal to grams of A over total grams times 100%. So let's say you had 100 grams total, and out of that 100 grams, 50 grams was A. What's the percentage? 50%. You see, so it should make sense to you. So if this were 100% acetic acid, so if for every 100 grams of total, I had 100 grams of pure acetic acid, then it'd be 100% acetic acid. Right? But vinegar solutions are typically around 5%. Yes. So what we're going to do is we could calculate this for each trial, but they didn't write 3 lines here, or 4 lines. It would be good to see it, but we'll see the spread here. So we'll get an idea of the precision here. Then we'll take the average here, and then we'll just use the average here. So was your question, do you need to do it for each one or do it for the average? All right, we're going to do it for the average for the percentage. It would be good to do it for each one and then see the spread there as well. But it's all right. The percentage of acetic, we'll just take the average molarity. So you're going to get whatever, X moles of acetic acid per liter. And so you know how to go from moles to grams, right? What do you use to go from moles to grams? You use, yeah, the molar mass. Not the mole ratio, but the molar mass. So we get grams of acetic acid pure. How do we go from liters of solution to grams of solution? What do we need? Yeah, we need to go to milliliters, and then we need to go to grams using the density. Problem is they don't give you the density of the solution. We don't know the concentration. The concentration is going to change the density. So this is a bit of information we're missing. So we have 2 choices. Choice 1 is stop here. Say that we're missing information, therefore we can't calculate the answer. Or step 2, or not step 2, choice 2 would be to estimate the density, just come up with some kind of guesstimated value for the density and come up with some kind of approximate answer for this. What should we do? Is some answer, even though it's not 100% correct, better than no answer? For you, what do you think? You would say no answer is better than an answer that's somewhat correct? Most people, if you need an answer that's 100% correct, as the science gets more and more complex, it's harder and harder to approximate. I remember during the there's just this recent study I was just looking at. There's a professor at Stanford, or UCSF, in the medical school there. Sometimes I listen to his YouTube channel, but I haven't watched the video. But he was saying that there were some adverse effects from the COVID vaccine, but at the time people were saying it's 100% safe. But how can you be 100% in anything, And so if you're waiting for 100% the correct answer, you're going to be waiting for a very long time, because even in quantum mechanics, solving the Schrodinger equation is so difficult that it can only be solved exactly for the hydrogen atom. Anything more complex than the hydrogen atom, what they have to do is they have to take the best guesstimate about what the wave function is like. And so they have different levels of calculations, and as the computers get more and more sophisticated, their calculations can get more and more accurate, but still the calculations are off. And so this is very common in science. What's very common is we make approximations. Mathematicians, it's very difficult for mathematicians because either the answer is right or the answer is wrong, but in science there's different levels of wrong. There's wrong with high confidence, or there's wrong with low confidence. It depends, with high precision, with low precision. So we have all these words to give us some idea of the uncertainty involved. Well, what they're telling us here in the lab is to do what? Yeah, they're telling us to guesstimate the density. In calculating the percentage by mass of acetic acid in the solution, assume the density. So we're going to make an assumption to be the same as pure water. That seems totally wrong. A vinegar, is that the same as pure water? No, there's a bunch of acid in there. Isn't that going to change the density? Yes, it does change the density. The question is, how much does it change the density by? So is this a decent approximation or a poor approximation? How much confidence can we have in this? And so to give you an idea of this, what would you estimate as the density of seawater? Would you say that seawater is close to pure water? No, the density. Would you say it's more dense, right? Because there's a bunch of salt dissolved in there. And so do you know what the density, the average density is approximately? No, 1.03 grams per milliliter. So if we assume that seawater was like pure water, we'd be about 3% error. Is 3% error livable or unacceptable? Well, it depends. For our Chem 4 calculations, this is acceptable, but we probably would rather use this. I'd much rather not use this. I would much rather use the density of acetic acid, but the density changes with concentration. So we're going to use this assumption, and we're going to keep in mind that we're going to have an error. In that error, sorry, I didn't turn off my phone. That error could result in being off a little bit. How much off? Not that much, maybe 1% or 2%. And so for us, that's acceptable. At least we'll get some kind of answer, even though it might have a small error associated with it. And the error should be fairly small. So going from liters to milliliters, that should be simple, right? 1,000 milliliters per liter. And then going from milliliters to grams, well, if it's the same as water, then 1 milliliter water weighs how much? 1 gram, 3 sig figs. So we're going to do it to 3 sig figs. And then once you get that, then what do we do? The final step is to convert the fraction into a percentage. How do you convert a fraction into percentage? Multiplied by 100%. So if we had a fraction 1/2, a fraction 1/2 would be converted into the percentage 50%. 1/2 would be 50%. In other words, 1/2 is 0.5 times 100%. It would be 50%. All right, any other questions on this? So you want to complete your calculations. What's a reasonable answer for acetic acid? Percent by mass is around 5%. Would be reasonable. All right, next we're going to take a look at experiment 11. Were there any other questions? All right, why don't you skim through experiment 11? Have you skimmed through it already? No? Yeah, normally, like for example at UCLA, not only do you have to skim through it, you have to really understand it because they give you a pre-lab quiz right at the beginning. But so what is qualitative analysis? That would be like a quiz question on, like, say if this were at UCLA. So you write like a short definition of what qualitative analysis is. So what is it?
Can I read off the paper? It's a lot of words.
Yeah, go ahead.
Uses systematic procedures for identification of species and investigative sample material.
Okay, so what we're going to do is qualitative analysis is just trying to identify the content or composition of things. So in this particular experiment, if I have a liquid here, I want to know what's inside the liquid. If it's deionized water, you know what should be inside here? It should be pure water. Unfortunately, our deionized water won't have ions, but it has, you know what it's contaminated with? It's contaminated with air. There's a little bit air dissolved in here. So aquatic life can survive. But there's also CO2 dissolved in here because there's CO2 in air. And CO2 lowers the pH of the water. Lowers the pH, meaning it makes the water more acidic. A lot of people were worried, well, if the CO2 levels get too high, then the oceans are going to be too acidic, and then it's going to destroy all the coral reefs. Have you heard that? That's one of the negative aspects, potentially, of that. And so they're thinking, okay, what can we do? Well, what we can do here is we can just be aware that the CO2 that's dissolved in here lowers the pH from normal. What's normal pH? 7. pH 7 is neutral. Somebody who had the alkaline water, was that you, Jason? Alkaline water, they want higher pHs. You don't want too high of pH. Like drain cleaner. Drain cleaner would have the pH around 14. And that cleans drains pretty well. But like alkaline water would be like pH 8, I think. Maybe 9, but 9's getting pretty basic. You don't want to go too high. But the pH of our DI water is 4.5. 4.5, from 7 to 4.5 doesn't seem like all that much, but the pH scale is like the Richter scale. The pH scale goes by orders of magnitude. And so if we go from pH 7 to pH 4, that's 3 orders of magnitude, which is 10 times 10 times 10, which is 1,000 times more acidic than neutral. But it's fine. We know that. Okay, but what we don't want in here are ions. But how do we know our deionizer is working? You know, can you tell by looking at this that no? There's a quick test that we do for deionized water. You know our quick test? We put an electrical circuit in here that's open. And what happens is, it's not a light bulb, it's a meter. If there's ions in the water, the meter will light up and tell us our water's bad because now we're getting electric current through our water. If you're getting electric current through your water, that means you have ions present. And the ions mean that the DI water is bad. All right, let's say our DI water is bad. But what we want to know is, what ions do you expect to find in the water? Do you know what ions you're going to expect to find in tap water? Well, if you look at there's a crust. Do you see this crust of mineral deposits on the tap here? Yes. What is that made out of? You know, this crust. And so what we want to do is we want to try to figure out what ions I can expect to find in tap water. I already know what ions I'm likely to find. Do you know what ions I'm likely to find? Probably one of the most common ions would be sodium ions. You know, sodium ions. Maybe some others. Chloride ions. Calcium ions, maybe. Hopefully not too much lead or chromium. You know, there's a big problem with chromium-6 contaminating the tap water in Central Valley, California, Hinckley, California. You know, so you definitely don't want that. For example, in Vegas, in Las Vegas, the tap water there was heavily contaminated with perchlorates. You know, perchlorate, what was the formula for perchlorate? ClO4 minus, but you know, that stuff is hard to get rid of because what can you precipitate? Perchlorates are all soluble. So they had a big headache. How are they going to get rid of the perchlorates out of the drinking water? And so they had a big celebration when they brought the perchlorate levels down to acceptable values. And then they showed all the city officials drinking the tap water, you know, confirming that it's perchlorate free. But perchlorates are a powerful oxidizer, and that was used in a rocket fuel and oxidizer plant just north of Las Vegas that ended up exploding. It's no longer there. It's a horrendous explosion that completely leveled the plant, killed 2 people. But anyway, what we're going to do is we're going to do some simple chemical tests. You know, we're going to use the chemical properties of certain ions to determine their presence or absence. This is qualitative analysis. Qualitative analysis is just trying to identify chemical species present. There's something else called quantitative analysis. And so qualitative analysis, ID, species, present. The results of a qualitative analysis are this. Positive means present. Negative means what? Yeah, you would think it's the opposite, but it's not the opposite. Negative means could not detect.
So it's there, but it's not strong enough to detect.
Yes, exactly. Could not detect. There could be 2 reasons you could not detect. It's absent, or
So small.
the quantity is so small it went unnoticed.
But that's like the number 2 we're using to see how small.
Exactly. It depends on the sensitivity of the test. We have something called the detection limit. So if it's below the detection limit, then we aren't going to see it. But it could be there. And each test is different. The detection limit isn't fixed. Some tests are highly sensitive. For example, the sodium test is crazy sensitive. Sodium test is so sensitive that people get false positives all the time. That is, they accidentally contaminate their sample with sodium and then boom, they got a positive sodium test. Other tests are so insensitive that it's easy to get a false negative. A false negative means it was there, you just missed it because either your technique wasn't good or it was below the detection limit. And so if we get a negative, it still might be there. We just don't know. But a positive is good. A positive means it's for sure should be there. But positive, could we have a false positive? Yes, we could have false positives too. But what we try to do is we try to have confirmatory tests to eliminate the chance for a false positive. And so somebody sat for a long time and figured this out. How are they going to test for the presence? This isn't a comprehensive list. In Chem 1B, we used to do a lot more ions than this. But we're going to just look for these 5 cations here. We're going to test for these 5. And for these 3 anions. And so this is limited. There's much more expansive schemes. So does our solution contain ammonium, silver ion, lead 2, barium, or manganese 2? And so I recommend skip for now the ammonium test. You can do this anytime. This is a single test. It's fast and can do any time. For now, we're going to go back and do it. We're going to start with B. B is very involved procedure. Testing for silver, lead, manganese, what was the other one? Barium. Yeah. Barium. So A might take you a few minutes, but B is going to take you multiple lab periods, maybe 2 lab periods. And so what we're going to do is we're going to look at the overall procedure first for part B. This flow chart here is for A. It's just a single step. The anions are also single step kind of reaction, so the anions can be tested individually. However, the remaining 4 cations have to be tested in this scheme. The reason it has to be tested in this scheme is because this scheme was developed to avoid false positives and false negatives. And so what we're going to do is we're going to take 12 milliliters. You're going to get more than 12 milliliters. So measure this out. And then save the rest for the other tests. A, C, D, and E, I think. On the one hand, we want to use a lot, because the more we use, yeah, the more precipitate we get, the easier it is to see things. But on the other hand, the more we use, the bigger the glassware we have to use. So rather than using test tubes, we have to use beakers. What would you rather use, a test tube or a beaker? Test tube's a lot easier, a lot faster to clean. A beaker is a lot more, and it's a bit more hassle. So, you don't want to use too little. Using too little means, we lose a little bit. Let's say our percent yield here was 90%. Our percent yield there was 70%. Our percent yield here was 40%. By the time we get to the end of this scheme, we have nothing left. You're supposed to get a precipitate and nothing happens. Why? Well, you lost. You lost a little bit at each turn. And by the end, you have nothing left. So 12 milliliters, that's about the max we'll want to use without having to switch to beakers. So the first step is we're going to add HCl and then heat it. Actually, we do it simultaneously. We heat and add the HCl, but I would say do it in steps. So 1A, we're going to add the HCl. So what happens to each ion when we add HCl? Well, silver ion likes what? This is a composite. HCl consists of what? H plus and Cl minus. It's a strong acid. H plus doesn't react in this case, just the Cl minus. So what we're going to get is AgCl plus H plus. AgCl is an insoluble chloride. And so we get a precipitate there. When we go to Pb2 plus also likes chloride, but it likes two chlorides in this case, and it'll form PbCl2 plus, actually just PbCl2 solid. Barium does not precipitate. So barium plus chloride yields Nr. Manganese does not precipitate, so manganese plus chloride yields Nr. Now, when you heat like sugar cubes in water, does more sugar dissolve or less sugar dissolve, or does it stay the same? In other words, is it easier to dissolve sugar cubes in hot water or cold water? In hot water. But not everything has the same response to water. And so in the second part, what we're going to do is we're going to heat silver chloride solid in water. And very little of it dissolves. Negligible amount is lost. However, when we heat PbCl2 solid in water, we can get all of it to dissolve again. But this is just like sugar cubes. And we want this to happen. What we want to do is we want to separate these two precipitates. So how do you separate silver chloride from lead-2 chloride? The way we separate silver chloride from lead-2 chloride is by heating it up. But just like sugar cubes, you're going to have to crush it. And so what you do with your stir rod is crush it and stir it to make sure you've dissolved as much of the lead. If you don't dissolve all your sugar cubes, it's easy to see. However, if you don't dissolve all your lead, it's impossible to see because of this. Silver chloride's white, lead-2 chloride's white. So you're going to lose some, but it's very hard to tell. So what you got to do is you got to keep crushing and then just notice, does it seem like anything else is dissolving? If it doesn't seem like anything else is dissolving, then you've dissolved all of it.
So we're only crushing lead chloride.
Yes, well, you have to crush both because the silver chloride isn't going to dissolve, just the lead.
You're crushing before we heat it.
No, you're crushing as you're heating. It's like trying to dissolve a sugar cube. How do you know when the sugar cube's completely dissolved? It's gone. How do you know when all the lead chloride's dissolved? It's hard to tell. So you just got to keep crushing it and keep crushing, and it seems like it's futile, then stop there. And then it's probably enough. You know, like 5 minutes or so. Be careful when you're crushing it because these test tubes have been abused. And what happens is, you know, what's the normal tetrahedral bond angle? What's the tetrahedral bond angle? Did you see what I just did? I just broke the test tube. What happens is people do this semester after semester, crushing this lead 2 chloride to get it to dissolve like the sugar cubes. And then all of a sudden, poke, all their solution drips onto the counter and they have to start over again, unfortunately. Also, lead is a heavy metal. We don't want to touch that. We don't want to get it on our hands. We want to avoid contact with lead. So we got to be careful with lead. The same thing with silver. Silver is also a heavy metal. Not only that, silver stains your fingers black. It doesn't wash off. And so what we have to do is we have to be careful here with the test tube. Be gentle with the bottom of the test tube. Otherwise, it's easy to poke a hole. I barely put any force on that. And the reason is people do this year after year. It tweaks the bond angles. The normal tetrahedral bond angle is, anybody? 109? Yeah. But each time you do this, you tweak it a little bit, tweak it a little bit more, tweak it a little bit more, and that's called mechanical. It's going to have mechanical failure. So what we do for glass is this. What I usually do to prevent this from happening is I take advantage of one of the properties of glass. Wow. Let's see my test. One of the properties of the glass is it softens as you heat it. When it softens, what happens is it releases the stress. So if you can soften it enough, let's say the bond angle got tweak. If you soften it enough, then the bond angles can relax back to their original position, like a 109. That process is called annealing. And so what we do is we just heat the bottom of the test tube, like in the hot part of the flame, and then get it to soften a little bit, and then cool it down slowly, and then it'll anneal. Don't touch hot glass, it'll give you blisters. But what it does is it makes it mechanically much more rigid, a lot less brittle. And so you could do that with your test tube too. You could just do a quick anneal. When you set it down, the hot end, point it away from you. This is a safety rule. Whenever you have a hot object, point it away from you because people tend to grab the end closest to them, and you want the cool end closest to you. Once somebody brought some glassware for me to check, and they handed the hot end to me, and then I grabbed the hot end to grab it to take a look, and then I ended up getting some burns. Blisters. But just be careful. And hot glass looks exactly the same as cold glass. You can't tell the difference. You know. So you could anneal this, at least one test tube if you want. You don't have to anneal all your test tubes. But if you're going to be pounding on the bottom of the test tube with a stir rod, then you should anneal it. All right. So what this dashed line means is solution. And what the solid line means, precipitate. So what we have initially are two precipitates. And so let me do this. What are the two precipitates? The two precipitates are PbCl2 and AgCl. And that would be solid. And then what we have to do is we have to heat it. We have to heat it so that the PB goes over this way and the AgCl goes this way. And what we're going to do is we're going to filter it using a gravity filtration setup. So for a gravity filtration setup, we have a funnel here, and we have a clay triangle. We put the funnel in the clay triangle, and then we get an iron ring. We'll put the iron ring like this. So this is our gravity filtration setup, and we'll put it on a ring stand. Like this. Okay, I'm missing one thing. I need a filter to capture the precipitate. And so the filter should be in a box. Yeah, the filters are over here. And they have different filters, and they have this code. This is 413 qualitative. I wish they would just put the explanation on here. You know, you have to go look up the code, what it means, on their website. But I have a round filter and a cone here. How's it going to fit in there? I just crush it in like this? Well, this is the technique that people recommend. Yeah. So you're familiar with that? So what we're going to do is we're going to fold it in half and then fold it in half again so we make a quarter. And then what we're going to do is we're going to put 3 sheets on one side, 1 sheet on the other to make a little cone like this. But what they say is to tear off a corner. Did they ever say why? Yeah, so I tried both. I tried tearing off the corner and not tearing off the corner, and made no difference. So I stopped tearing off the corner. It takes time. The next thing we do is we need it to stay. You know, it keeps popping out. And so what I do is I just get a little bit of DI water, wet it down, so that it adheres to the surface of the funnel. And so now it's stuck on the inside of the funnel. That's good. This. Okay, and now I'm ready to filter. So what I want to do is I want to capture the white silver chloride precipitate in the funnel here. And what's going to drain out of that funnel is this. And so the white precipitate goes here, and the solution goes. Now this solution we don't throw away. A lot of times when people do filtrations, they throw away the what we call the filtrate, the liquid that comes off here, or the supernatant. But in our case, we don't want to throw this away. We want to place the liquid that drains out of here into a clean container. Because that liquid that drains out of there is going to contain our lead, barium, manganese. We have to filter this while it's hot, because if it cools down, the lead will reprecipitate out of solution, and then we'll capture both silver and lead. If we capture both silver and lead, it screws up this test. We get some really weird results. So we filter it hot, and then what we want to do is we want to rinse it with hot water. And so what you need to do is you need to set up a hot water bath. Do we have hot plates here? There are hot plates there? Well, maybe I might get a hot plate. If not, then we need to set up a hot water bath on our ring stand. Setting up a hot water bath, I do it like this. I get the biggest ring I can find, and I fit the biggest beaker I can into that ring. So I have a 400 here and a big ring, and so this should protect it. And then what I'm going to do is I'm going to set up 2 rings here. One ring I'm going to put the wire gauze on like this. And that's going to hold the beaker up. Now this ring is stuck. Screw. And flip it like that. All right, I'm setting it up like this so the beaker doesn't accidentally get knocked over like that. This is to protect it in case there's an earthquake or something. And then I wanted to adjust the height because I want what part of the flame to hit the gauze here. I want the hottest part of the flame to hit the gauze. And so I need to adjust this so the cone hits that. And so I'm probably going to lower this to about here. And then lower this here. So what I'll do is I'll put some water in here. I like DI water because it doesn't leave hard water deposits. So we fill it up with enough water so that we can cook our test tubes here. So that should be enough, like halfway. So. And then this is probably what you want to do first because it takes a long time to get water hot, at least boiling. And so set this up first. Get your water going. We might have boiling chips. If not, then we'll just have to deal with it without them. All right, we're also going to wash our precipitate. What we want to do is, our precipitate is going to be wet with supernatant solution. And what we're going to do is the first washing will be combined with the supernatant solution. We don't want to lose any lead, barium, or manganese. We want to make sure we get all of it. And so what I'm going to do here is I'm going to filter it into a clean container. So I can capture all the supernatant. And then it's wet with supernatant, and I don't want to lose that supernatant. So my first wash is going to be with hot water. So maybe I'll get a dropper and then just wash off the precipitate with hot water and capture any supernatant here. That's the first wash. But I'm going to give it a second wash as well, maybe a third wash. The second wash I'm going to discard because the second wash should be just almost just water. Should be very little supernatant. And what I don't want to do is I don't want to dilute this. If I add a whole bunch of water to this, I'm just shooting myself in the foot, so they say, because I'm just going to make it harder and harder to detect. The more dilute it is, the harder it is to detect. The more concentrated it is, the easier it is to detect. And so the first wash, you save. The second and third wash, you discard. You don't discard it down the sink, though. You're going to discard it in the waste over there. So we're going to keep a big waste beaker at our station so we don't have to walk back and forth all the time. We want the precipitate to be clean because if the precipitate is contaminated with any of these ions, it's going to screw up the tests here. And so this precipitate has to be pure. That's why we're going to wash it. So what we're going to do is we're going to put a waste beaker under here, and then we're going to take some sodium hydroxide and add the sodium hydroxide directly to the precipitate in the filter. Any excess sodium hydroxide can drain into waste. And what should happen is that sodium hydroxide should convert this white precipitate into a black precipitate. What that is it's a metathesis style reaction. So let me write down what's happening with this. So let's assume that our precipitate is pure. It's been thoroughly washed and it's nice and clean now. And what we're going to do is we're going to take our silver chloride precipitate and add hydroxide to this. And what we're going to form here is we're going to form silver hydroxide and sodium chloride. This is a double replacement reaction here. This silver hydroxide is tricky because when you look at this, we have one precipitate, silver chloride, and we have another precipitate, silver hydroxide. And so is there really a driving force? Doesn't the dissolving the silver chloride cancel out the precipitation of the silver hydroxide? And the answer is it depends on which precipitate's more stable. It turns out that silver hydroxide becomes more stable when it does this. This is A. In part B, what we do is we take 2 silver hydroxides and we decompose that into 1 silver oxide. And what else is remaining? Hydrogens and oxygens, which makes H2O liquid. This is an acid-base reaction here. So the first reaction is metathesis. The second reaction is a Lewis acid-base reaction, which we really haven't talked about as much. And so if we get a black precipitate here, that means we tested positive for silver ions. So that means we definitely had silver ions present. You guys should test positive because your known solution is going to contain all the ions. So if you're testing negative, unfortunately something went wrong. So the first part 1 is all knowns, all positives. Part 2 is unknown. And silver ion might not be present.
So, looking at the pattern of this procedure, we're just isolating each element one by one.
Exactly. We're isolating them one by one. However, we have to go into sequence, because if we go out of sequence, then it doesn't quite work. And so, carrying this on, we have 3: lead, barium, manganese. Now we have to get rid of another one. So who's going to be eliminated this time? Lead. And lead is easy to eliminate because we're going to add iodide. Lead loves iodide. And so let's take a look at that. And so in this next reaction here, we have lead, and potassium ions are unreactive, but lead likes 2 iodides to form a yellow precipitate of lead 2 iodide. Barium could care less. Barium plus 2 iodides yields Nr, no reaction. Manganese doesn't care either. Manganese plus 2 iodides yields Nr, no reaction. So the only thing that reacts here is the lead. Well, that's fine. So now comes the next point, which I didn't talk about earlier. We have to have complete and clean separations. So another problem is this. What if you don't precipitate all the lead out? How do you know when you've precipitated 100% of the lead out? It's hard to tell because what happens is this becomes cloudy. And you're adding drops, and you can't tell, is it getting cloudier or not because it's so cloudy already? You can't see. So sometimes what you have to do is you have to wait for it to settle down. When it settles down, then the top clears up. So it's like the fog settling down and you can see blue sky. When you can see blue sky, then you can add a drop and see if you get more cloud formation. We're looking for cloud formation. Yeah. The same thing happens here, but it's a lot less difficult because when you heat it up, it causes the small crystals to coagulate to form bigger crystals. So when you heat precipitates up, they tend to settle more rapidly, more easily. If you're having an impossible time here, you could also heat this up a little bit, but you have to wait for it to cool down. But you got to wait for the cloudiness to subside and then add another drop of potassium iodide and see if you get more cloud formation. You want to keep adding potassium iodide until there's no more cloud formation. Now, how do you write a procedure for this? You know, how do you write a procedure for this? Because everybody's unknown is different. And so what they're doing is they're writing a procedure to fit everybody. So it's like, okay, how do you make one pair of shoes fit everybody in the class? Yeah, just pick the biggest size possible, right? But is that going to be good? A good fit? No, so this procedure is written like that. Okay, we're going to have a size 15 shoe for everybody. But does that work effectively? It doesn't work effectively. So what I do is I completely ignore how much they say to add. You know, they say to add this many milliliters. I don't care how many milliliters. That could be way too much or it could be way too little. Maybe, you know, somebody else walked in with size 18 feet. You don't know. And so what we do is we adjust the amount visually to do what we want. So I completely ignore how much HCl they say to add. You know, I don't care how much HCl they say to add. I keep adding HCl until I stop seeing cloud formation. Now, of course, this is, for some people, that's too much to deal with, so they'll just follow the procedure. So you could just follow the procedure as written, but your results will be a lot easier to analyze and interpret if you could adjust the amounts accordingly. And adjusting the amounts accordingly is not that difficult. Here, how much Ki you add, you keep adding it until you stop seeing precipitate form. That's the right amount. Not the amount they say in the book. This is what gets people in trouble. Sometimes the amount they say in the book is too little, and they don't get all of it out. They don't get all of it out, and it screws up all the rest of the results, and they come up to me and say, what happened? You know? And then I say, start over again, because something screwed up, unfortunately. And so sometimes it's an easy fix, but sometimes it's not. And if you have to, let's say you get to the last step here, and you have to start over again, you don't want to do that, because you've already invested so much time. Or you get to the last step here and you poke a hole in your test tube. And then you have to start over again. The one benefit to starting over again is it goes a lot smoother the second time around. Or the third time around. Yeah. You need to transfer the precipitate over here. So how do you transfer it? Well, you use a little bit of wash. You know, you use a little bit of wash to transfer it and to wash the precipitate. You know, sometimes it's hard to get all the precipitate over. If you don't get all the precipitate over, don't worry about it. Just as long as there's no precipitate contaminating this. So I expect a little bit of loss. You know, I don't expect to get every little piece because it takes way too much time. But the same thing here. This precipitate is contaminated with supernatant solution or filtrate solution. So what we need to do is we need to wash it. The first wash goes here. The second and third wash we discard. But do we need to wash this? No. Second or third time, we don't need to wash this. We just need to wash this the first time so that we don't lose any supernatant. Because we're not doing any subsequent reactions with this. So as long as we see the yellow precipitate here, we're done. The yellow precipitate there means we're tested positive for lead. So we wash any residual supernatant over into the solution over here, and we're left with barium and manganese. So how do we separate barium from manganese? Well, yeah, sodium, what's this called? Nobody.
Hydrosulfate?
No, that was a common mistake on the test. Not hydrosulfate. Sodium bisulfate. Sodium bisulfate is a very common salt. So we're going to use some sodium bisulfate. And so what happens when barium comes into contact with bisulfate? With sodium, nothing, but with bisulfate, something does.
For the first step, the sequence code, is that correct?
Yes. So what barium does is knocks that hydrogen off, makes barium sulfate, which precipitates, and we're left with the hydrogen ion. Manganese doesn't do anything. So manganese plus bisulfate yields no reaction, NR. Just calcium, strontium, barium, like sulfate, along with silver, lead. Mercury. All right, this one we're only going to give one wash. The one wash is so we don't lose any supernatant solution containing manganese. So that one wash will combine here. We don't have to do any further washes here because we're done with barium analysis. This is a positive test for barium ion. Okay, so we do one wash. We get the manganese all in this beaker or test tube. And then what we're going to do is we're going to remove the manganese out. Hopefully we get a precipitate here. A lot of times people get to this step and there's nothing left. They lost the manganese somewhere else in one of the earlier steps. But hopefully we get a precipitate. The precipitate that we're looking for is the hydroxide. And so if we take manganese, likes hydroxide, actually 2 hydroxides, and this is going to form a precipitate of manganese 2 hydroxide. The metathesis reaction. This manganese 2 hydroxide is a light brown PPT. Okay, we're going to wash this one though and discard. We want to wash it because we don't want any contaminants, potential contaminants, here for the next step.
How many washes?
This one, like 2 washes.
For barium, it was only one wash.
Yeah. This is hard to wash, this precipitate, because this precipitate's like gelatinous. It's almost like transparent, and it's you don't want to wash it too much because you might think it'll disappear. You know, it's like a ghost precipitate. It's not so solid. It's kind of low density, gelatinous. And so the washing is not so easy. So two washes max probably.
So you washed off that,
Yeah.
and you spread the solution and add the statistics.
Yeah, right. Okay, then 6A, what we're going to do is the nitric acid is going to dissolve it. So if we take the manganese 2 hydroxide solid plus the nitric acid, we'll need 2 nitric acids. This is going to form manganese 2 nitrate, which is soluble salt, plus 2 waters. And so how much nitric acid do you add? How much nitric acid you add? You add enough to dissolve all your precipitate and then stop. You don't have to go overkill. Well, actually, you need a little bit extra.
So you want to get rid of the precipitate.
Yeah. And then we're going to use this. Nitric acid is dangerous. Because nitric acid is a strong oxidizer. What color does silver stain your skin? Black. Nitric acid stains your skin yellow. So if you have yellow splotches, you've spilled some nitric acid on your skin. It's also a strong oxidizer. Sodium bismutate. This is called sodium bismutate. Sodium bismutate is a even more powerful oxidizer. The reason it's more dangerous is it's a fine powder. If you have a fine powder and you sneeze, what's going to happen? You're going to create a dust cloud. And if you inhale sodium bismutate, it's going to cause some serious damage to your lungs and throat and whatever else. Your skin is probably okay, but it's a strong oxidizer. It's like, do you want to go and inhale chlorine gas? Have you ever inhaled chlorine gas? Yeah. It's bad. And so the sodium bismutate is in the red cap plastic bottle over there. I'm going to put it inside the hood. So in case you accidentally do make a dust cloud, it gets sucked out the hood. And so I'll move it there. But what you're looking for is you are looking for this solution to turn into grape juice. Like purple grape juice. That's permanganate. Yeah, so you're looking for a liquid, not a solid precipitate. This dashed line means it's a liquid. So you're looking for a little bit of grape juice. If you have a little bit of grape juice form, don't drink it because permanganate's also a powerful oxidizer. Don't drink it, but that test that is positive for manganese 2+. Just a little bit of grape juice, a drop or two. That's all we need. At the end, yeah.
Is it actually grape juice?
No, it's not grape juice. It looks like grape juice, artificial grape juice. All right, we're going to focus on part B right now. I'll talk about parts A, C, D, E next time. All right. So you can work with a partner if you want, or you can work solo. If you work solo, it's good because then you can get the experience, the full experience of doing it. If you work with a partner, make sure each of you clearly participate in each step because you're going to be doing this solo next, okay? That is individually. I think the known solution might be back there, or you might get it. All right, the known solution, cation unknown solution, part B, you get from the stockroom. Don't use all of it. We're going to save some for the other test. Just use 12 milliliters of it. Bring a 50 milliliter beaker. This is the safety goggles lab.